It's a company originally from Calgary. They have an office in Pittsburgh. As the name said, Desanders is their main job. Mr. Sisto had a bachelor's degree on industrial engineering from University of Purdue yesterday, and also hold an MBA from University of Pittsburgh. He has almost more than 12 years experience as a field engineer in Calgary, and comes with great experience over here. And I had a conversation with what they are doing. It's very interesting applied physics and fluid dynamics. Pay attention to what he says and prepare for questions.
Great. Well, thank you very much for having me. And yeah, anything confuses you as I'm going through this, raise your hand. I'll plan on asking questions and making this back and forth as much as it is just like Ali said, our company is Specialized Desanders. Founded in Calgary about 10 years ago, expanded to the U.S. about 2 years ago, and chose this area to start our initial footprint into the U.S. market. I'll explain a little bit more as to why later on. But we're a 50-person company with 3 U.S. employees, including myself. So a lot to do with very few people. But like Ali said, it's a pretty neat case study in applied physics and math and engineering. Thought I'd talk a little bit about my career progression first and foremost. I started with Halliburton right out of college. There are several different routes you can take after graduation, and one would be the service company route versus operators and other consulting type of tracks. But going to a service company has some unique benefits, and one in particular is the formal training program. Halliburton offers several different services, and so engineers out of college participate in a 6-month training program. It gives you a very broad understanding of the industry and all the different processes. So you can start off as a jack of all trades before you decide where you want to specialize. It gives you a great opportunity to network with other engineers that are starting out, and people change jobs and companies, and you never know where they're going to end up. So starting early with a network is very important. And this does increase your personal value to future potential employers. So there are a lot of small companies out there with very little in the way of training. So if you can get on with a company that has a very solid, well-developed training program, that becomes part of who you are as an oil and gas engineer, and you can take that wherever you go. So some of my best customers were trained as Halliburton or Schlumberger engineers, and really wherever you go in your career, you take that training, and it's invaluable, especially going to a smaller company later on down the road. As a field engineer starting out, or in the field, like the title would suggest, thing is you get your field training early in your career where you have very little perspective or understanding of what you're doing. And as you progress through your career, you have less and less opportunity for field experience because you're busy running companies or programs or managing people. So getting the field training while you can is important right out of college. That could be your only opportunity to get your hands dirty, to talk to folks in the field that have decades of experience practically, which you can't get from the training program, or really that gets lost when those people retire. So as much knowledge transfer as possible through asking questions, paying attention, and networking with those field personnel can really pick up a lot more than what the formal training program or your education would allow. Also allows you to meet customers or meet other people from other companies that you're working with in the field. Some of the folks that are running things today, the key decision makers in several of the gas companies in the area, were field engineers that didn't pick up out in the middle of nowhere in Virginia with me 10 years ago. So customers and even competitors can become people that are movers and shakers of the industry very quickly, and certainly with that big gap in people in the industry, the 50 and 60-year-old folks that are getting ready to retire, having that 15 or 20-year chasm where now you're expecting 25, 27, 30, 35-year-old engineers to take on those roles that otherwise seasoned employees will be taking on. Allows you the opportunity to move up very quickly, and also allows for people in key positions to be those that you came up with. So you never make any enemies, because even the competitors, like I said, could make or break you 5 years later when they move to an operator or something like that. From there, it took a little bit of an interesting move, because there were so few people working in the industry in the Northeast back in 2004, 2005. Engineers were expected to interface with the client. So you gain some experience in explaining technologies, and really taking on almost a sales type role as you do, putting together proposals. I was tapped to be an in-house engineer with one of our top clients to manage a contracted project, a 2-year coal bed methane project. And so being put in the customer office gave me the opportunity to be the point person for just about whatever they bring me. It gives you a chance to be more than just someone that sits behind a computer or does design. If that's the kind of engineer you want to be, there are several opportunities out there, but it's certainly not the exclusive path for an engineer. If you're the kind of engineer that likes to talk to people and be more social, there are opportunities to do that. And one of those opportunities I found was more of a sales track. In service companies in particular, the engineers are the salespeople because you're selling a technical product. So where you're able to do that, where I was able to become an account rep and then later on a sales manager, led me to my sales and marketing role that I'm in today. I'll talk a little bit about what my supervisor, who was supposed to be here, had leave on a family emergency, so I'll go through his career progression in much less detail because I didn't live it. So, talking a little bit about specialized desanders, you got to start with hydraulic fracturing, because the sand that you deal with is the sand that's pumped down a hole during the fracturing process. So, this is the ground, and then there's several layers of rock underneath the ground. I'm not telling you guys anything you don't know. But then the horizontal well is drilled to that reservoir. When they frack the well, they'll pump water with some chemicals in order to carry sand into the formation, pump it at such a high pressure that they're going to induce a fracture in stages along this lateral. Those fractures in which you pump sand will then become conductive pathways for the oil and gas to get to the well more quickly, get to the pipeline more quickly, to allow you to sell it and make money more quickly. On a scale of what they're doing today in the Northeast, we're talking about an average of 50,000 pounds of sand per stage, and anywhere from 25 to 60 stages per well. So if we talk about a 30-stage well, for example, 50,000 pounds, we figured it was 1.5 million pounds of sand. And then what our clients in Western Canada have found is that if you produce back during the first few months 1% of that sand, you make the best long-term well. And the reason for that is while you're pumping the sand down the well, some of it inevitably is going to settle out in the bottom of this lateral. And over 2 miles at times, even a small layer of sand can add up to a significant amount in the way of pounds of sand. Also, when you're pumping these fractures, near the wellbore, there is some sand that is put into those fractures. And when the well is turned around back to production, you reach a critical velocity where this sand is going to be lifted and carried out. Some sand is going to come out of that near wellbore in the formation. And to the tune of, say, 1% of that sand, if you can produce back 15,000 pounds of sand, you are in a sweet spot as far as cleaning up your wellbore and also moving the sand from the near wellbore when you're ready for it. So this presents a pretty big problem in that sand can be very damaging in a lot of ways. So this is what our customers have dealt with for years. In Texas, in the 50s, they're producing mostly formation sand. Now we're pumping millions of pounds of sand into the formation. You get some of that back. So the problem became is how do you manage that sand on the surface? And what folks were doing traditionally was using a vertical, what they call a sand trap. What that sand trap did would bring in the flow from the well here, liquid, sand, gas, at very high velocities. And it would hit a baffle plate, so a piece of metal sticking down in the middle. It would kind of mix around in here and leave, hoping that during that transit time there, the sand would settle out in the bottom of that vessel. I'm going to move this back a little bit. Nope, this is in the corner. This is wildly ineffective because you have turbulent flow throughout. Gas and liquid are constantly churning up the sand. It's like trying to settle out sand in a bottle of water while you're shaking it. It's really hard to do. So 3 guys in Canada who were engineers working for a major oil company thought we have a better way to do this. They went out and designed it, put it on paper, went to their boss, asked for a little bit of money to build a prototype, and like any good boss, he said, no, we don't have the money, but if you want to do it on the weekends, go ahead and try to make a business out of it. And that's exactly what they did. They built a couple of prototypes with a couple of outside investors. They proved it in the field. They refined it over time and built this company. What their concept was a horizontal pressure vessel that would achieve laminar flow and increase the transit time for sand to fall out, like it was sitting in a glass of water on your desk. And the way this would work is flow the well horizontally into the pressure vessel. The outlet is going to be off the top of the pressure vessel 20 feet later. Also inside of our original design was an inverted veer, which is just a piece of metal hanging from the top. What that did was allow for a gas head under pressure and a liquid phase to flow along the bottom independently. So now where your gas and liquid was all commingled in this environment, now it was separated quickly and velocities are slowed dramatically. Because you have a 3-inch ID, interior diameter inlet nozzle, going to a 20 or 24-inch pressure vessel, you have the same volume going through a bigger area, you reduce velocity by the square of the radius. So when you do that, your gas just flows along the top, your liquid flows along the bottom in a laminar state because it's at much lower velocity. Your sand hits that fluid line, then as your liquid flows through, the sand just settles out like I said, it's sitting in a cup of water on your desk. There's no energy to lift it up, it settles out over time and starts to build up in the bottom of this vessel. So if you look at it here, this is what I'm talking about. Flowing in through the inlet, flowing out through the outlet here, and the rest of this assembly is to release pressure during the clean out. And this cap here is an opening where once it's full, 1,000 to 2,000 pounds of sand later, you're able to clean it out by either scraping it out or sucking it out with a vacuum truck. I have a picture of that, I think, actually. Oh. Talk about this. This is what sand can do to you, right? So sand gets into your production equipment, scours the metal, starts to release gas unexpectedly, something switches on, creates a spark, and that's one of our best customers in Canada because they use one of our units on every well to stop the sand at the wellhead before it can cause damage to the production equipment. On a much more minor scale, you can see kind of here where it's washed through a valve, washed out the body of a strainer of sorts, washed out another valve there. Sand at high velocities can basically cut through metal like it's not even there. Silica is very hard, harder than steel, and like I said, at high velocities, when it's pounding against the side of a valve or where your piping does like a 90-degree turn, that sand hits it. Over time, it washes it out, and you have an uncontrolled release of gas, liquid, explosion. It can be very severe. But this is what it will look like in the field. This is one of our trials in the Marcellus. which shows it connected to the wellhead here, flowing in, and then flowing out to the production equipment, production separator. When it needs to be cleaned out, you run in with a hose. This vac unit sucks out the sand, and 40 minutes later, you're able to start all over and go back to flowing. Any questions so far? Yeah.
How often
All depends on how fast you're making sand, right? We hold 1,000 to 2,000 pounds, so if you can make it in 2 hours. We have people take slugs of sand overnight, and alarms go off, and everybody gets woken up at 2 in the morning, and we have to set up a clean out or shut in the well to keep it from carrying over. Typically, we see the first couple of weeks, you're cleaning it out once every couple of days. The next couple of weeks, you clean it out once or twice a week. And by the second month, you're cleaning it out every week or less. By the third month, you're barely cleaning it out, but you're still making enough sand that, and not in there, it would have damaged it. Okay, so because we're an engineering company, we're always looking for 2 things. Continuous improvement, well, 3 things. Continuous improvement to where we can make this process even better and more efficient. A couple of years ago, can everybody see what I'm drawing over here? I'm hoping. Not completely. A couple of years ago, our CEO figured